Alright, hey guys, this week I'm supposed to help you with number 41 on chapter 29. And the question is, the four 1 gram spheres shown in this figure are released simultaneously and allowed to move away from each other. What is the speed of each sphere when they are very far apart? Okay, so first things first, this is a conservation of energy problem. So the initial energy of the system was the final energy of the system, and if we expand that, the initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy. So since in the beginning we're holding it there's no kinetic energy in the initial, and so in the end, because they're so far apart, they have no interaction with each other, which means that there is no potential energy at the end. So we get the initial potential energy is the final kinetic energy. And then if we expand this, we have the potential energy between each of these charges, which is U of 1 and 2 plus U of 1 and 3, etc. And this is what you get, and this equals the final kinetic energy, which is just the kinetic energy of all of these added up. So for Kf, since they're all the same but they're just going in different directions, but this question is not asking for the direction, just the magnitude of the speed at the end. So the equation to find the U of the potential energy is U equals K Q1 Q2 over R, right? So all of these have the same Q, but they don't all have the same R. So between 1 and 4 and 2 and 3, the radii are different. And with the Pythagorean theorem, we can easily find out that it's root 2 centimeters right here, or the radius between these points and these points. And so what we can do is group all the ones that have 1 centimeter radius or distance, and then group the ones with root 2 centimeter distance. So that gives us U of 1, 2, U of 1, 3, 2, 4, U of 2, 3, and we can group these, add this to U of 1 and 4, and U of 2 and 3, and group these, equals 4kf. And now these are all the same. They all have the same radius, or the same distance, and they all have the same charge. So we can just do 4k q squared, since all the q's are the same, over r1 plus 2 k q squared r2, which is this distance. This is r1, equals 4kf again. So then I guess just fill all this out, and we get for k, which is a constant, 10 to the negative 9 squared over, convert the centimeters into meters, so we get 0.01. This is multiplied by 4, so same thing over here. 2k 10 times 10 to the negative 9 squared over, now this is R2, so it's root 0.02 for the radius. And yeah, so then there's just some punching into the calculator, and for this term you get 3.6 times 10 to the negative 4, and for this term you get 1.27 10 to the negative 4, and so the initial, or when you add these, you get the initial potential energy. So U initial equals 4.87 times 10 to the negative 4 joules. And now, since we have this U initial equals K final, we can set this equal to K. So 4.87 times 10 to the negative 4 equals 4.5 mv squared. So then we can simplify the K side. So 4.87 times 10 negative 4 equals 2. And then the mass of this thing, of the charges, are 1.001 kilograms. And this is divided by v squared. So then just do some math. Get v equals 4.87 times 10 to the negative 4 divided by 0.002, and this is square rooted, and in the end we get v equals 0.49 meters per second. There you go. Go team.